Good morning, everyone. Good morning, class. Good morning, everyone. Am I audible and visible properly? Just inform me. Good morning. Good morning. So, how are you all doing? I hope you must be doing good and great. Reply quickly, faster. Dinesh, good morning. Be quick, be very quick. Good morning, Manish. Prasad ji, good morning. Good morning, everyone. Okay. So, audible and visible properly. So, can we begin the class? Joyo, ex Joyo. Shagiri. Good morning, bache. Good morning, everyone. Chalo, ठीक है. So we'll begin, and today we'll begin with Thomson's atomic model. Good morning, everyone. Okay, that's good. The class is active now, and that's what you are best at, being active. Good morning. Chalo, we'll begin. Na? So today we'll try to discuss Thomson's atomic model, Rutherford's atomic model, and we'll try to complete electromagnetic radiations also. This is the task, na? And I hope that some questions from these topics will be coming in the coming test as well. So prepare properly and do the practice of questions as well. Okay. So I'm beginning with that. So last time we were discussing cathode ray tube, and in that cathode ray tube, Thomson was able to find out cathode rays, and he found that cathode rays are negatively charged particles, and later on they will be named as electrons. Okay. Now people asked Thomson that you are the first one to look into the internal parts of the atom. So why don't you give a model for that? So Thomson said, okay, I'll give it. Okay, let me try that. So we'll begin with Thomson's atomic model, which is also called plum pudding model or watermelon model, which is also called plum pudding model, or yes, good one, or watermelon model. Okay. So according to Thomson, he gave certain points regarding that. You know? He said that atom, keep writing, an atom is positively charged sphere. An atom is positively charged sphere in which, yeah, resin pudding, plum pudding, one and same thing. Okay. So according to Thomson, what is an atom? Atom is a spherically charged, atom is a positively charged spherical, it's a positive charge sphere in which negative charge is uniformly embedded, in which negative charge is uniformly embedded. So actually Thomson was saying that his model is something like this. Hai? He said that atom is spherical and it is positively charged as well, in which these electrons, the negatively charged particles, are uniformly embedded. Okay. Second point you should write down is that according to Thomson, atom was having uniform distribution of charge and mass. Mass was also uniformly distributed. I mean, whether you take here or this piece or this part, anywhere, you will see that mass is uniformly distributed. There is a uniform distribution of mass as well as charge. Getting it? So uniform distribution of charge and mass. Next point you can write down that, I mean, according to this model, I mean, this is a model which is going to explain the stability of atom. I mean, anyone can visualize pretty well that in a uniformly charged, positively charged sphere, we can have some negatively charged particles dispersed properly. Now, this is a stable model. Okay. the amount of negative charge and amount of positive charge is almost same. Amount of negative charge is equal to amount of positive charge. Only then it can be neutral. Like if I touch anything, any panel or any pen or whatever, my body as well, all these things are what? Neutral. And rather, Thomson was telling the world basically that all these things are made up of atoms only, and since all these things are neutral, that means the thing which they're composed of, like say atoms, they must also be neutral in nature. Yes or no? So negative charge is also equal to positive charge. That will make the entire atom neutral. So what he said that an atom is a positively charged sphere in which negative charge is uniformly embedded. Second point, he said that the mass and the charge are uniformly distributed, and according to him, the atom is stable. So his model was explaining the stability of an atom. You'll find that neither Rutherford nor Bohr will be able to explain the stability of atom, because their model was having certain deficiency. No doubt about it that this model is also having some deficiency. But as of now, it is able to explain theoretically the stability of an atom. Next point, he went on to find out the radius of an atom, and according to him, the radius of atom was approximately 10 to power of minus 8 centimeter. A very important piece of information. Okay, you should keep in mind. So that was Thomson's model. So when you give a model, so model is basically a rough sketch of the reality. Since we can't see the atoms, we still can't see that. So leave apart that Thomson will be seeing that stuff. So he prepared a plan for that, a model of that. And based on that model, he gave the theory part. Now, science means not only theory. Theory has to be verified through experiments. So he asked his student, Rutherford, to verify his model through an experiment. See, understand that anyone can give any theory. Anyone has a right to give any theory or hypothesis, but all these theories and hypotheses have to be tested in the laboratory. If your theory is able to explain that experiment, well and good. Otherwise, the theory has to be discarded. And if you don't want to discard the theory, you have to improve upon that so as to match the experimental values. Okay? So he asked his student Rutherford to perform an experiment and see that what I'm saying is correct or not. So Rutherford performed the experiment. So Rutherford's alpha scattering experiment. Rutherford's alpha scattering experiment. Okay, are you getting that? So what Rutherford did, he basically took a lead box. And in that lead box, he placed radium. Now, radium is radioactive, and it is a source of alpha particle. What is alpha particle? It is a helium nucleus, 4He2 and 2+. It's nothing but helium nucleus. Now, they have a good penetrating power comparatively. Okay, so now this is an alpha particle ray. He put a slit over here so that one alpha particle can pass, one at a time kind of thing, or a very few particles can pass. He placed a gold foil of dimensions of 10 to power of minus 4 mm. Now 10 to power of minus 4 mm is very, very thin, very, very thin. He made it so thin so that at least the alpha particle can pass through it. They can pass through it. He could have taken the thicker foil, but in that case, it would not have been able to pass the foil. Now, why gold? Because gold is very much malleable and ductile material. There is no element in the entire periodic table which is more malleable and ductile, and we basically need what? This much amount of thinness. Yes or no? That can be achieved only by gold. Now, why we are using lead? Because radium is radioactive, and if the person who is performing the experiment, he need to come out alive outside the laboratory, then he had to make sure that he is not affected by the radiations. Okay. So we will put this in the lead box. Lead is having a very high density. That means, the particles cannot pass through the lead. Okay. Very good. And he put again the same thing, a fluorescent screen out there, a fluorescent screen. Okay, again, like say made up of zinc sulfide, and if a charged body will strike there, it will show the scintillation, the spark or the glow. Okay, so he was performing and he found that yes, there was scattering all around. He was finding the scintillations or the sparks everywhere around, but most of the scintillations were focused here. I mean, as we move away from the center part, the number of scintillation kept on decreasing. So I mean, he prepared a full-fledged chart for that, and he found what? That most of the, if alpha particles are coming from here, if alpha particles are coming and they are all positively charged, all alpha particles are helium nucleus, sans of electrons, there are no electrons in that. So he found that most of the alpha particles are passing undeviated. Most of them are passing undeviated. This everyone knows from the, like say, 11th class onwards. So most of them are passing undeviated, and the particles which was passing near the center, they were deviated. They were deviated. More closer to the center, more the deviation. More closer, more the deviation. And he also found out that, out of 10,000 particles, one alpha particle was also rebounding back, was going and was rebounding back. So this was basically his observation. So based on this observation, he will do some conclusions. So let us do that stuff. Okay. So what were his conclusions and what were his observations? Let us find out that. Okay. So we'll place it over here. So the observations and conclusions. Observations and conclusions. Okay. Chalo. Aa The first observation, what is the first observation? That most of the alpha particles pass undeviated. Write down, please. Most of the alpha particles pass undeviated. Be quick. Most of the alpha particles are passed undeviated. So what can you do the conclusion of that stuff? What is the conclusion from this stuff? When will the alpha particle pass undeviated? I mean, anything pass undeviated basically. When there is nothing in front of it, if there is an obstacle, it will not pass undeviated basically. Na? For example, if I fire something in the water, it will have a trajectory, I mean, which very soon it will keep on coming down. But if there is nothing in front of me, it will keep on moving forward in a straight line. Yes or no? Yes. That actually means at most, since most particles are passing undeviated, which means what? Most part of the atom is empty. So conclusion is most part of the atom is empty. So atom is actually almost empty, and later on he found that that 99.9% of an atom is actually empty. Okay. So okay, chalo. Second point. Now he found that second observation was that the few particles were deviating, which were passing closer to the nucleus. So what is the meaning of that? When will these positive particles deviate? They will deviate only when the center is having a positive charge. Yes or no? The like charges will repel each other. So there will be a deviation. There will be a deflection. Okay. So the second observation is that few particles deflected at angles less than 90 degree. At angles less than 90 degree. So what is the conclusion? If they are deviating, that is the only possibility is what? That the center must be positively charged. Center must be positively charged. Center is positively charged. This center he called nucleus. Yes or no? The third observation was one in every 10,000 particles, or in some books it is written as 20,000 particles. You take whatever you want to take. So what I'm saying, one in every 10,000 particles, out of 10,000 particles, one particle was rebounding back. Now, this was the most surprising observation. It's just like that. Rutherford said it was like if you fire a bullet through a sheet of paper. Now, what do you expect? What you will expect? Atoms are very, very thin, very, very thin. The dimension of 10 to power minus 8, 10 to power minus 8 centimeters. We have just seen that. So if you fire a bullet, the alpha particle, which is very heavy, yes or no, then most of them are passing. That is understandable. But why the hell one is coming back? How it is coming back? It's like that you are seeing a bullet being fired on a piece of paper and the bullet is being reflected back by the paper. So that was like something amazing. So he concluded basically that, to tell you one thing, this is a table tennis ball and this is basically an iron ball. There's a table tennis ball, this is an iron ball. So if a table tennis ball goes and strikes the iron ball, will it rebound back? Will it rebound back or not? It will definitely rebound back. But if I say that the iron ball is moving this way and strikes the table tennis ball, will the iron ball rebound back? No, it will keep on moving ahead. Yes or no? So if you want something to come back, if this ball is striking a very heavy ball, only then it will be coming back. Otherwise, it will keep on moving ahead. So if you want something to rebound back, make sure that this thing should be lighter as compared to the thing with which it's going to make a strike. Yes or no? This should be very heavy and dense also. This should be very heavy and dense. Yes or no? So if I throw a pen on this wall, it will keep on coming back. Yes or no? But if I fire a very high velocity, having high momentum, cannonball, it might penetrate this thing. Yes or no, beta? Okay, that actually means what? Since it is coming back, an entire atom is empty. Entire atom is empty. Almost entire atom is empty. That means the mass should be somewhere. Where? Mass should be where? At the center. Almost entire mass must be located at the center of the atom. Over here, there's nothing. This is nothing actually. So charge is where? At the nucleus. Now this charge cannot stay in air. It needs something to stay. Yes or no? It needs something to stay. Some mass must be there. If there is a charge, there must be mass. Since it is having a positive charge, that means most of the mass should also be at the center. So center of the nucleus is having almost all the mass of atom. That means almost all the mass of the atom is located at the center. Is that clear? Is that clear? All the three conclusions, is that clear or not? Good one. Now see this thing. So now people asked Rutherford to give his model. So Rutherford said it is quite simple. See that I'm saying that in an atom, center is positively charged and it contains almost all the mass. Now we all know that anything is made up of atom itself and everything around is neutral. That means atom should be neutral. Atom should be neutral. Yes or no? If there is a positive charge, I'll need an equal amount of negative charge also. Equal amount of negative charge. But I cannot place it at the nucleus. So I have to keep it where? Outside the nucleus. So he said that the negative charge is actually outside the nucleus. So when he said that, he told Thomson that, Thomson, your model is incorrect, because experiment says that positive charge must be at the center and it cannot have negative charge, because if the negative charge is also inside the nucleus, in that case there will be no deviation, because this nucleus will become neutral, and if this is neutral, alpha particles will keep on passing undeviated. Yes or no? They'll keep on passing and there will be no deflection, no deviation. Are you getting it? He said, Thomson, according to your model, which is uniformly charged and uniform mass is there, that either all the alpha particles should pass or no alpha particle should pass through it. He said, what I'm observing is that almost all alpha particles pass, few particles deflect. That deflection is only possible when we have got a positive charge. Yes or no? And that also means that electrons cannot live inside the nucleus, because if you put the electrons inside that, it will become neutral. If it is neutral, the alpha particles which are coming over here, they will not be deflected. Only a positive charge can deflect a positive charge. Yes or no? Getting it? Good one. Very good. Very good. So, but there was a problem. The moment you keep the electron outside, Rutherford was in problem now, because the elementary physics tells us that the positive and the negative charges are going to attract each other. There is nothing which can stop it from falling. So Rutherford was like gone with the wind. He was like surprised. I cannot put the electrons inside. And if I put the electrons inside, this experiment what I have done, I mean, this theory of mine will not match it. But the moment I put it outside, the electron will fall inside and the existence of atom will be in danger immediately. So this was the scenario the scientists were actually going through. This kind of confusion, the conundrum, the enigma. So like Rutherford was thinking that what I can do, electron has to be outside and nucleus has to be positively charged. Now what I should do? So he thought about the solar system. He said that we are having sun, and across sun, I mean, there are many planets which are revolving peacefully without any problem. The reason is that the elementary idea of physics again tells us that if there is a planet out there, its centripetal force is balanced by the centrifugal force. This is a centripetal force, this is a centrifugal force. So when this inner force and the outside force are balanced, the planet keeps on revolving uniformly. Yes or no? Yes. Yes. So he brought the same idea of solar system into his atom. He said, why don't I make my electron or the negative charge particle revolve? If it will revolve, again, the same concept I can apply. F1 and F2 are equal. Once they're equal, they will keep on revolving uniformly. And he was very happy. Oh my God, I should be getting a Nobel Prize for explaining the structure and the stability of an atom. But at the same time, there is a very powerful theory. According to Maxwell's electromagnetic wave, EM wave, electromagnetic wave theory. Please write down. According to electromagnetic wave theory, if a charged particle accelerates, or say revolve, or say jump, it is the established law of electromagnetism, a very powerful. Whenever a charged particle, whether positive or negative, whenever a charged particle will accelerate, revolve, or jump, it will lose the kinetic energy. Very good. Very good. So what are the implications of this theory of Maxwell? That over here, the problem is that the sun and the planets, they are neutral. Sun and the planets are neutral. So the Maxwell's electromagnetic wave theory does not apply over there. Yes or no? According to electromagnetic wave radiation, so basically, if planets and sun are neutral, this theory will not be applicable here. So here, the F1 is equal to F2, and they keep on working eternally. But over here, electron is charged as well as nucleus is also positively charged. This is negative, this is positive. And here, if they try to revolve, they should, according to the theory of Maxwell, they should start losing the kinetic energy. And if they do it, rather than moving in a circle, they will keep on coming down. They will lose the energy and they will spiral down into the nucleus. And they found out that time taken to do so is 10 to the power minus 8 seconds. So in 10 to the power minus 8 seconds, the entire atom will be gone. Yes or no? So despite telling a beautiful thing that an atom must have a nucleus and which contains positive charge, electron should live outside. But the problem was that if the moment you put them outside, whether stationary or revolving, either way, the electron cannot survive. It will fall inside the nucleus. That means Rutherford model was not able to explain the stability of atom. Yes or no? Yes or no? That F1 equal to F2, centripetal force equal to centrifugal force, is doing good as far as planets are concerned, because they are like all neutral. But out here, according to the Maxwell theory, any charged body, and they are charged bodies, if they revolve, jump, or accelerate, they will lose the kinetic energy, and if they do it, they will have to fall inside the nucleus. That means immediately, the moment the atom is formed, it will be disintegrated also. It will be gone. So, like the world of science was in puzzle, to kare kya? What to do from here? Yes or no? So this will be the idea of the entire chapter. This entire chapter is basically about who the hell will explain the stability of atom. So we are right now almost like say in the year of 1906, 1906, 1907. It will take at least 20 more years to explain the stability of atom. Bohr will come, and many scientists will come. Almost all the scientists you are going to study in this chapter are almost all of them Nobel Prize winners. Now, these Nobel Prize winners were not able to explain a simple phenomena of the stability of an atom. Agree? Chalo. Now, so write down please shortcomings of Rutherford's model. Shortcomings of or drawbacks of Rutherford's model. Drawbacks of Rutherford model. The first one. Now you know that stuff. It is not able to explain the stability of atom. It is not able to explain stability of atom. It is not able to explain stability of atom. Second point, it could not explain the hydrogen spectrum. It could not explain hydrogen spectrum. I mean, all the things we will study after Rutherford, he was not able to explain. How he will explain that poor chap? He was the first one to actually look inside the structure of atom. So, I mean, that world behaves quite differently. It's a weird world out there, okay? And that world of atom does not follow the world of our own world. Okay? Chalo, aa jao. So, the second point, he could not explain the hydrogen spectrum. Third one, he could not explain the electronic distribution in atoms. He could not explain the electronic distribution in atoms. Okay, so there are the shortcomings. Okay, now let us move forward, and now let us do something bit different, because they will be asking you in the coming test also. So we'll discuss isotopes, isobars, isotones. Can you discuss that quickly, all of you? Chalo, aa jao. We all know that we represent an element X, say, by say a subscript and a superscript of A. This Z is called atomic number. Atomic number, which means what? Number of protons, which means number of protons, while this A is called mass number, which is nothing but N plus P, neutrons plus protons. Now, we also know that in the previous lecture, we have seen that mass of electrons is almost negligible as compared to the mass of protons and neutrons. So when you have to calculate the mass of an atom, I mean, we neglect the contribution of electron. We only take what? We only take the mass of protons and neutrons, which is given by the mass number. Yes or no? Chal, aa jao. Now come over here. First thing we'll discuss is isotope. Isotopes. So what are isotopes? Isotopes have basically what? Same value of Z. Same value of Z, but different value of mass number. They will give you basically options. You have to pick up the right option. Getting it? Okay. So let me give you some examples. So can we have some examples of isotopes? Like say carbon, carbon, carbon. Atomic number has to be same. 6, 6, 6. And A has to be different. 12, 13 and 14. Just check basically the Z is same, but A is different. And you will get a pair of isotopes or a group of isotopes. Hai na? Yes, very good. HDT also. I can take one more example. H, like 1, 1, 1 and 1, 2 and 3. This thing is called protium. This is called deuterium and this is called tritium. This is called tritium. Yeah, very good, very good. Similarly, students, we can define isobars. What are isobars? Who will tell me what are isobars? Now, isobars have same value of A, but different value of Z. Different value of Z. That means N plus P should be same, but Z, what is that P? P should be different. Yep, good, very good, very good. So can you give me some examples of that? Give me some examples of that. Can I have carbon 14 and 6 and nitrogen 14 and 7? Will it be okay? We can also give you example like say potassium 40, 19 and calcium 40, 20. Any example you can take, but where the A is same but Z is different. They will give you the options. Just pick the right options. Okay. Okay, here we go. Next we can have next one is isotones. Isotones. So beta, what are isotones? Isotones which have got same number of neutrons. Very good. Which have got same number of neutrons. Yes or no beta? Neutrons. Which is what? N will be what? A minus Z. Yes or no? Number of neutrons, or say A minus Z. A minus Z should be same. So what is A? A is N plus P. What is Z? Z is again P. So minus P. Minus and minus cancel. This will cancel and there will be N. So either we can have same number of neutrons or you can find out A minus Z value to be same. Chalo, help me with that stuff. Give me examples of the isotones. Who will give me the example of isotones? Be quick. Examples of isotones. We need same value of N minus P. Who will give it to me? Be quick. अरे इतना time थोड़ी लगाएंगे यार. You just find out any two species in which we are having A minus Z as same. Chalo, I'm giving you carbon 13, 6. So, if I go with A minus Z, it will be what? 13 minus 6 what? 7. Can I go with that? N. 14, 7. So again it will be like say 14 minus 7, 7. Yes or no? Yep. Can I say oxygen 15 and 8? So 15 minus 8 again what? 7. They are all isotones. All of them are isotones. Huh? Acha, Rame is saying argon and calcium for isobars. That is also possible. If you want that, we can have argon 18 and this will be 40. They all are isobars. But I'm asking right now the isotones. Getting that? All of you understood? All of you? Okay. Similarly, we can have now, there is something called isodiaphers. Isodiaphers. Who will tell me what are isodiaphers? Come on. What are isodiaphers? Be quick. Isodiaphers. Be quick. Isodiaphers are the species for which N minus P is same, which have got the same value of N minus P. Or you can say A minus 2Z. A minus 2Z. You can see that A is what? N plus P and Z is what? P. So minus of 2P. N plus P. So this will be N minus P. So if N minus P is same, it will be called isodiapher. Or you can simply say, just do A minus 2Z. A minus 2Z. That will be fine. Chalo, aajao. Give me some examples now. Give me some examples. Chalo, aajao. With the help of common sense. Come on. So let's take anything. Can I take carbon? Carbon is basically 6. And I'm focusing upon that A minus 2Z should be 1. A minus 2Z should be 1. So I can make it 13. So A minus 2Z will be how much? Double will be what? 12. 13 minus 12 is what? 1. Yes or no? Come on, can I take something else? 15 and 7. 15 and 7. Will it do it? This will double will become 14. 15 minus 14 will be again 1. Come on, get me something more. Get me something more. 1708. 1708. Yes or no? Dekho. Double will become 16. So 17 minus 16 again 1. They're all what? Isodiaphers. Isodiaphers. Hagena. I believe we can take some more examples. Just allow me. Few more examples, like say, can I have 40 potassium and 19? So A minus Z will be A minus 2Z. A minus 2Z will be what? 40 minus 38, 2. 40 minus 38, 2. Come on. Give me something more. Give me something more. Carbon 14, 6. Will it do? Will it do? 14 minus 12, again 2. So they are also a pair of isodiaphers. Yes or no? Getting it now? So whatever they gave, you can handle that? All of you? Great. Very good. Going good. So can we go to the more interesting part right now? Chalo aajao. Okay, come. Now let's do one more, and this is bachcho isoelectronic. Isoelectronic. Bolo. Isoelectronic. What are isoelectronic? Which have same number of electrons. Same number of electrons. Okay? Good. Very good. So give me some examples. Give me some examples of isoelectronic species. Help me out. Is it so or not? CH4, NH3, and H2O. Are they isoelectronic? Are they isoelectronic? Boys and girls, come on, be quick. Jaldi bolo yaar. So number of electrons over here will be how much? 6 plus 4, 10. 7 plus 3, 10. 2 plus 8, 10. Good one. Very good. Manisha, very, very good, bache. Bahut अच्छे. Naveed, very good. Excellent. Acha, can I have like say something more? N3 negative. N3 negative. Number of electrons out here will be how much? 10 again. 10 again. What else? Anant, very good, beta. Anant, very, very good. 10. I can say O2 minus, F negative, and neon, and Na plus, and magnesium 2 plus. Yes or no? Is it okay? All of them are having 10 electrons. All of them. 10, 10, 10, 10, and 10. 10, 10. Yes or no? Good one. Okay, we can have one more. Anant was giving, so I'm writing that. And this, so you will be using in Bohr's model also. Like what? Hydrogen, helium plus, lithium 2 plus. Yes or no? Come on. Number of electrons. Number of electrons, how many? 1, 1, and 1. Beryllium 3 plus. All of that. Yep. Anant again. Very good, Anant. So now let's come to one more thing. And that will be better. The last thing, and that is called isosters. Isosters. So what are isosters? Which have same number of electrons and, or say as well as same number of atoms, Yes or no? They have got same number of electrons as well as same number of atoms. So tell me, are these group, this group, are they going to form isoster? Yes or? See, here the number of electrons are same. That is okay. One part is satisfied. But how about this one? We have got 5 atoms. Carbon plus 4 hydrogen. 4 atoms and 3 atoms. They are not isosters. I'll tell you one thing. Are these isosters? Will they form isoster? Will this group be called a group of isosters? Yes. 1 atom each, and number of electrons 10. So please put this example out there. Good, very good, very good. Acha, how about this one? Can you call this group as isoster? 1 atom each, and number of electrons also same. So this group will also form example of isoster. Okay, come on, tell me. CO, carbon monoxide, Cn negative, and N2. Do you think they are isosters? Do you think they are isosters? Two atoms, and two atoms, and number of electrons. Come on, that will be 6 plus 8. How much? 14. Come on, 6 plus 7 and 1 negative. That means one more. How much? 14. How about this one? 14 again. Yes or no? So they have same number of atoms and same number of electrons. Yes, they are isosters. They are isosters. Okay, one more example. We can take the most important one, CO2 and N2O. CO2 and N2O. Will they form isosters? Will they form isosters? Yes. Oh, they will be. They will form isosters. 3 atoms, 3 atoms. 3 atoms and 3 atoms there. And number of electrons, let's see that. So number of electrons will be 6 plus 16, 22. 22 electrons. How about this one? 14 plus 8, 22 electrons again. So same number of atoms and same number of electrons. They are isosters. Clear hai ki nahi hai? Yes or no? Be quick. Everyone. Great. Very good. Very good. हाँ, HCl and F2, 17 and 1. हाँ, very good, beta Charan. Very good. Very good. Okay, great. So, I mean, you can expect the examiner to give you some questions from this topic in the coming test. So, prepare it properly. Go through the concepts, and that is it. So, PK143LV. ये कैसा नाम है यार? Yeah, calcium plus 2 and K plus. Correct. Correct. Okay, now. So, let us do some questions, I mean, based on that. But in weekend syllabus, I believe that you will be having probably cathode ray tube, properties of that cathode rays, and the quantization of charge. That is what something we have discussed. Yes, and specific charge, their series kind of thing, that thing, mass of electron, mass of proton, all that stuff, and Thomson's model, the Rutherford's model, these isosters, isotopes, isotones, all this, and probably we will be having the syllabus till Planck's theory. Okay, so that means this is today's Thursday. So whatever we do till Saturday, it will be all coming in syllabus. Okay, so prepare well. Just prepare well. Chalo aajao. Basic not in weekend, sir. Maybe like few questions from that also will be there. है ना? हाँ, I'll send you syllabus also. I'll send you syllabus in the group as well. Don't worry at all. That I'll do. That I'll do. So come on now. So few questions I'm doing, and I'll give you the explanation and the formula while solving the question. Okay? Okay. Didapya, I mean, you will get all that information in the group as such. Don't worry at all. Okay? They'll give you everything in the group. Don't worry. So let's see. There's a question. An element X. An element. Please write down. An element exist as 3 isotopes. An element exists as 3 isotopes, X1, X2 and X3. X1, X2 and X3 with their mass numbers as 10, 12 and 14 respectively. With their mass numbers as 10, 12 and 14 respectively. This mass number is equivalent to beta atomic weight. Right? The weight of an atom is because of the neutrons and protons, which are given by whom? Mass number. And their percentage of occurrence. And their percentage of occurrence. And their percentage of occurrence in nature is, their percentage of occurrence in nature is 80%, 15% and 5% respectively. 18%, 80%, 15% and 5% respectively. There are three isotopes of the element X, X1, X2, X3. Their atomic mass is basically 10, 12 and 14, and their percentage occurrence is 80%, 50% and 5%. I'll call it, boys and girls, P1, P2 and P3. Find its average atomic weight. Find its average atomic weight. Come on. Find its average atomic weight. No, PK143. यार एक तो अपना नाम लिखो, ये कैसा नाम है तुम्हारा? PK143 समझ नहीं आ रहा. That will be your isobar, not isotope, है ना? The example you're giving, they are examples of isobar. Okay, chalo. Find average atomic weight. So let's do it. It's very simple. Whenever they give you that isotopes can be like 2 in number, 3 in number, or 4 or 5, 6 isotopes, don't worry at all. Don't worry at all. The formula for the average atomic weight will be like, I'm taking the isotopes, this X1, X2 and X3, and their percentages P1, P2 and P3. So what you will do, you will find out the total weight upon total number of atoms, or say elements. This will be like, say, X1 P1 plus X2 P2 plus X3 P3. If one atom has a weight of 10, 80 will have a weight of 80 into 10. If one atom has a weight of 12, 15 will have 15 into 12. And similarly, one atom has a weight of 14, 5 will have what? 5 into 14. Upon what? P1 plus P2 plus P3, which will always be what? 100. Which will always be 100. So this will be 80 into 10 plus 12 into 15 plus 14 into 5 divided by 100. The total number of atoms present is always 100 in terms of percentage, bache, okay? So when you will solve it, you will get 10.5. 10.5. Since most of the atoms are like, say, of X1 only, these are very, very less. Very, very less. So this will have more weightage. This will have more weightage. Yes or no? So answer will be near to 10 only. Someone was giving me 12. No, 12 is not possible. Yes or no? Are you getting that? Similarly, if I give you a question, like say chlorine exists in the form of two isotopes, Cl35 and Cl37, and their occurrence is in the ratio of 3:1. Their occurrence in the ratio of 3:1. Find the average atomic weight of chlorine. Find the average atomic weight of chlorine. Now, one chlorine is have a weight of 35. 3 will have how much? 35 into 3 plus, since one chlorine has a weight of 37 and we need one only, so 37 into 1. So total number of particles are how many? 3 this one and 1 that one. So 3 plus 1, 4. 3 plus 1 will be 4. So when you will solve it, you will get 35.5. 35.5. Very good. So this you remember already. Very good. But if they give you something else also, I believe you can do it. Yes or no? So be prepared with that kind of stuff. Practice these questions a little bit and you'll be fine. Yeah? So let us quickly do now. Let us quickly do the electromagnetic radiations. Electromagnetic radiations, which we will call in short EMR, electromagnetic radiations. Okay, this will be using, without that we cannot understand Planck and Niels Bohr also. Okay, chalo aa jao. So according to Maxwell, we all know that when a charged particle accelerates, please write down. According to Maxwell, when a charged particle accelerates, it will lose its kinetic energy it will lose its kinetic energy. It will lose its kinetic energy in the form of electromagnetic radiations. Electromagnetic radiations. Okay. Electromagnetic radiations. Full stop. These radiations are propagated. These radiations are propagated in the form of wave. These radiations are propagated in the form of wave. Full stop. They are made up of electric field and magnetic field. They are made up of electric field and magnetic field, which are perpendicular to each other. Which are perpendicular to each other. Which are perpendicular to each other, and also perpendicular to the direction of propagation of the wave. To the direction of the propagation of the wave. So what happens, bache? So you know that whenever a charged particle accelerates, or revolves, or I say jumps, I told you na. So in either way, suppose for example, if an electron will jump from here to here, it will lose the energy in the form of electromagnetic radiation. Yes or no? This radiation is the topic of core basically in the hydrogen spectrum, Bohr's theory, and ahead of also. Okay. So whenever an electron jumps or accelerates or like say revolves, it will keep on losing the kinetic energy in the form of electromagnetic radiations. Okay, beta? Okay. Chalo, theek hai now. So like since these are EM waves, and like all waves, there are certain properties. So let's do that. So properties of EM waves. Properties of electromagnetic waves. Properties of electromagnetic waves. So the first one is wavelength. This wavelength, boys and girls, written as lambda. And what is that? Understand this thing. Achha, I forgot that thing. I was supposed to draw the diagram of electromagnetic radiation. So let's say we are having this as the electrical field and this as the magnetic field. So this electrical field is vibrating in the perpendicular plane and the magnetic field is vibrating in the horizontal plane. Okay. So this is supposed to say electrical field and this will be called magnetic field. So they keep on doing the undulations. Alternatively, a changing electrical field induces magnetic field and the changing magnetic field induces a electrical field. So they keep on propagating together. And this is the direction of the propagation of the wave. So this is the direction of propagation. Electrical field is perpendicular and magnetic field is also perpendicular in the horizontal direction. Yes or no? And they are perpendicular to each other also. This is called electromagnetic wave. Okay. Okay, come now over here. So wavelength. So if I take a wave basically, you will see that this distance of one wave cycle is this one. This is called lambda. Or you can take the distance between two consecutive crests also is called lambda, or the distance between two consecutive trough is also called lambda. They're all wavelength, same thing. Okay. And you will need some conversions also. For example, like say 1 angstrom is equal to 10 to power of minus 10 meter, equal to 10 to power of minus 8 centimeter. Also that 1 nanometer will be 10 to power of minus 9 meter, will be equal to 10 to power of minus 7 centimeter. You will need it. Note it down. And 1 picometer is 10 to power of minus 12 meter, which is equal to 10 to power minus 10 centimeter. Okay. Learn this thing. This is very, very important. Extremely important part. We will be doing the numericals based on these conversions, है ना? So please do them carefully. How? Now, femtometer we don't need it. We don't need femtometer. It won't be required, है ना? But that is 10 to the power minus 15 meter, na? Remember that. Okay, chalo, come on. Now see that there is something called second part. It's called frequency. It's called frequency given by nu. Hai na? What is frequency? It is the number of wave cycles passing through a point, hai na, in 1 second. Suppose what I'm saying, this is the point, and if through this point, like say this is a wave cycle. This is the wave cycle, and like say 10 wave cycles pass through this point, then the frequency will be 10 hertz or 10 per second. The unit of frequency is basically hertz or per second. Remember that? So it is basically the number of wave cycles passing through a point per second in 1 second. If 40 wave cycles pass through a point in 1 second, the frequency will be 40. Okay? Okay, great. Come on. Now next point. Achha, over here, since all the electromagnetic radiation. Achha, bachcho, can you give me some examples of electromagnetic radiations? Some examples of electromagnetic radiations. Come on, be quick. Jaldi bolo bachcho. Jaldi likho yaar kuch to. In short, write down. In short, write down. Gamma rays, X-rays, UV rays, visible rays, infrared rays. Yes, microwaves, radio waves. All of them are example of, yes, correct. All of them are the examples of electromagnetic radiation, and all these electromagnetic radiations, they travel with the speed of light. 3 into 10 to the power of 8 meter per second. All of them have the same speed, and this C is also equal to lambda into frequency. This is the relationship. Please tell us the table. I'll tell the table. Don't worry at all. I'll tell the table. Whatever you require, important part, I'll give it to you. And can I say that lambda will be equal to C upon frequency. Now you know that over here, from this part, C is constant. So can I say lambda is inversely proportional to frequency? Very, very important conclusion, which also means that if lambda will increase, that means frequency will decrease. If lambda will decrease, then frequency will be higher. If there is an electromagnetic radiation whose wavelength is higher, then the frequency of that radiation will be lower. Are you getting it? Okay. Okay, good one, very good. Okay. And then boys and girls, there is one more thing, and that is basically third point is wave number. Wave number is given by nu bar. This nu bar is basically beta 1 upon lambda. It is the number of wave cycles present in unit length. Number of wave cycles present in 1 unit length. For example, wavelength is suppose say 10 meter. Then what is wave number? How many waves are there in 1 meter? Unit meter. Okay? Unit length means 1 meter. So there are wavelength is 10. So wave number will be what? 1 upon lambda equal to 1 upon 10. That means 1 by 10 waves are there. 1 by 10. Yes or no? Good one. Similarly, if I say this wave number is say, the lambda is say 10 to the power of minus 3. 10 to the power of minus 3 meter. So what will be the wave number? Wave number will be 1 upon 10 to the power of minus 3, which means what? 10 to the power of 3. That means in 1 meter, there will be 10 to the power of 3 wave cycles, 1000 wave cycles. Okay? Achha, anyone remembers from the 11th class previously that where do you use this wave number? We will be using this wave number where? In the hydrogen spectrum and the Bohr's model, where they know that this is equal to 1 upon lambda equal to R Z square, 1 upon N1 square minus 1 upon N2 square. Remember that or not? So beta, whatever we are learning right now, right here, will be utilized, will be all utilized later on. Yes or no? Yep, correct. Rydberg's formula. Very good. So this is the thing we will be using there. Okay? Now chalo. Then there is something called amplitude. And amplitude is basically, I'll draw a diagram. It is the maximum displacement from the line of propagation. This is the line of propagation, horizontal line, and this is the maximum displacement called A. This is called amplitude, up or down, whatever it is. And one thing, according to Maxwell, again write down that intensity of the radiation is proportional to A square. This you have to learn, bachcho, at any cost. Okay, beta? Okay, good, very good. Now quickly coming to the electromagnetic spectrum. So it is the arrangement of the radiations in the increasing or the decreasing order. In the increasing or the decreasing order of what? Frequency or wavelength. So सबसे पहले इधर आएगा, most of them, cosmic rays, very, very important. Then will come gamma rays, then will come X-rays, then will come UV rays, then will come visible spectrum of visible rays or visible light, then will come infrared rays, and then microwaves or micro rays, and then there are radio waves. This is the entire spectrum. And remember that over here frequency is there, and suppose we are having lambda. So as you go from left to right, remember that from here the frequency keeps on decreasing, and if the frequency keeps on decreasing, lambda keeps on increasing. Yes or no? Now tell me one thing. Who will have the highest frequency among them? Write down the short. Who will have the highest frequency? Come on, girls and boys, be quick. Cosmic will have the highest frequency. Acha, who will have the highest wavelength? Come on. Highest wavelength. The answer is cosmic. I mean, for the highest frequency, answer is cosmic. And for the highest wavelength, answer is radio. This radio will have lambda maximum, but frequency minimum, because I know that if lambda is maximum, frequency will be minimum. And over here for cosmic rays, frequency is maximum, that means lambda will be minimum. Yes or no? Agree or not? Acha, tell you one thing, among gamma ray, X-ray and UV ray, who has the maximum frequency? Among gamma ray, X-ray and UV ray, which has the maximum frequency? Come on. Maximum frequency, gamma ray, X-ray, UV ray. Come on. Gamma. I mean, as you keep on moving from left to right, frequency decreases. And the frequency decreases, wavelength increases. Remember that? Okay, chalo, come on, tell me. Who will have highest lambda, highest wavelength among the visible, IR and micro? Among all these three, which will have highest wavelength? Micro will have the highest wavelength. As you keep on moving right, the wavelength keeps on increasing. Yes or no? Good one. Very good. Now let us focus somewhat upon this visible range. This visible range, I mean, learn this value. I mean, this range of wavelength vary from 400 nanometer to 700 nanometer. In some books, it is written as 380 to 690, something like that. But I mean, the 400 over here and 700 here will be doing good justification. And this is our Vibgyor line. Okay. So as you go from left to right, remember that the frequency keeps on decreasing, but lambda keeps on increasing. So now tell me one thing. Among this Vibgyor, who has maximum frequency? Who has got maximum frequency? Frequency is maximum for violet, which also means lambda will be minimum. But as you keep on moving from left to right, the wavelength increases lambda maximum, and if lambda is maximum, frequency will be minimum. Yes or no? Frequency will be minimum. I mean, this though we will be using, bacho. I mean, in Planck's theory also, we'll be using that in the black body radiation also, and a photoelectric effect also, and spectrum also. So do it very, very carefully, bacho. Very carefully, है ना? Yes or no? Acha, tell you one thing. Among blue, green, and yellow, which has maximum wavelength. Blue, green, yellow. Yellow will have the maximum wavelength. Very good. That means you have understood that stuff. Okay. Now just revise that, boys and girls. Okay. I'll catch you on Saturday. That is a very important lecture. Don't miss it. It's a very, very important lecture. Okay. Bye. Bye-bye, everyone. Have a great day ahead. Bye-bye.